All right, let's dive right into this explainer and check out the absolutely incredible engineering that allows the Nancy Grace Roman Space Telescope to maintain extreme precision while staring out into the vast, unending cosmos. Because, when you have an observatory tasked with settling some of the most fundamental questions in astrophysics, we're talking about the true nature of dark energy or finding hidden exoplanets, well, close enough simply isn't going to cut it. Today, we're going to look at the exact mechanisms, the specific software requirements, and the frankly microscopic mathematical corrections that keep this massive telescope perfectly locked onto its targets. So here's our roadmap for today. First, we'll look at the Roman Space Telescope itself. Then, we'll break down the 60 milliarcsecond requirement, followed by selecting optimal guide stars, dodging the spoiler stars, and finally correcting geometric distortion.
Starting with Section 1. The Roman Space Telescope, and its genuinely massive view of the cosmos. Roman has this incredibly massive 0.281 square degree field of view. To put that into perspective, it's designed to capture at least 100 times more of the sky than the Hubble Space Telescope can in a single shot. But it does this while still maintaining that same iconic Hubble-like resolution. When you map that footprint out against something like the Andromeda Galaxy or the Moon, you realize it's just a breathtaking expanse of space to capture all at once.
Now, to pull this off, to capture 1 billion galaxies over its mission lifetime, Roman utilizes 18 separate detectors. Specifically, these are H4RG10 detectors, all configured together in this massive array. And it does this using a 2.4-meter primary mirror, which is actually the exact same size as Hubble's. But here is the major catch. When your field of view is this incredibly wide and your resolution is this sharp, just stabilizing the spacecraft becomes a monumental engineering challenge. Literally any tiny wobble gets magnified across that massive field. That brings us right to Section 2, the 60 milliarcsecond requirement. Let's define exactly what extreme accuracy means here. The magic number we need to talk about is 60. More precisely, 60 milliarcseconds. This is the absolute positional accuracy requirement that the Science Operations Center's Planning and Scheduling Subsystem, we'll just call it the PSS from here on out, must hit. And just to give you an idea of how mind-bogglingly small that is, a milliarcsecond is 1,000th of an arcsecond. And an arcsecond? That's 1/3600th of a single degree. We are talking about an impossibly tiny sliver of the sky. This strict 60 milliarcsecond requirement basically boils down to two main components. First off, we have the known positions of the stars themselves. We are so incredibly lucky that humanity has the Gaia DR3 catalog, right? Because that gives us the celestial positions of most reference stars to within roughly 1 milliarcsecond of accuracy. So great, we've got a highly accurate map to start with. But the second component, that involves field angle distortion effects. These are errors that creep in from the physical geometric distortion of the lenses plus corrections for velocity aberration. So, moving to Section 3, selecting optimal guide stars, using the PSS and the flight software. The PSS really is the unsung hero of our story today. It's the system responsible for analyzing that vast catalog of known stars we just mentioned, and then picking the absolute perfect guide stars for the flight software to lock onto. It has to ensure these selected stars fall into a very specific brightness range for whatever observation mode is currently being used. Think about it. If the star is too dim, the telescope literally can't hold its gaze. But if it's too bright, it totally saturates the detectors. So here's the exact sequence of how this lock-on happens. Step 1, the PSS selects the best candidates. Step 2, the flight software takes what are called guide window exposures. And finally, Step 3, the flight software calculates the centroid position. It has an algorithm that specifically hunts for the star's exact center within a tiny 3x3 pixel region on the detector. If it can accurately find that centroid, Roman can stay locked, stable, and ready to do some science. But it's never that easy, is it? Let's go to Section 4, dodging the spoiler stars, or as I like to think of it, filtering out the adversaries. Enter the spoiler stars. These are essentially cosmic photobombers. Because Roman's field of view is so wide and peers so deeply into space, a perfectly chosen guide star might have a neighboring star sitting right next to it. And if that neighbor is close enough and bright enough, its light bleeds right over, completely contaminating that delicate 3x3 pixel centroid calculation the flight software is working so hard to perform. So what's the danger zone? Well, the flight software's algorithms reveal a critical threshold of 4 pixels. After running extensive simulations, scientists found that a spoiler star critically ruins the centroid calculation if it sits within 4 pixels of our target. Once it crosses that line, the spoiler star directly overlaps the guide star's point spread function, which is basically the physical shape and spread of the star's light on the detector. It totally confuses the software, causing the telescope to lose its precise tracking lock. To make absolutely sure this never happens during actual flight ops, the PSS rigorously validates its algorithms. The team generated these massive simulated star catalogs. They tested guide star magnitudes of 11, 13, and 15, and then purposefully threw potential spoiler stars at them, ranging from a bright magnitude 6 all the way down to a fainter magnitude 15. They placed them at random distances, ranging from 1 to 16 pixels away. By running these intense stress tests, they verified exactly when the tracking algorithm holds up and when it breaks. This allows the PSS to intelligently filter out any guide stars that have dangerous photobombers lurking a bit too close. All right, let's look at our final hurdle, Section 5, correcting geometric distortion. This is really the microscopic climax of the whole operation. So even if we pick the flawless guide star and completely avoid all the spoiler stars, we still have to deal with the physical reality of the telescope's optics. Wide-field instrument simulators have shown that geometric distortion, the natural physical warping of light as it passes through the lenses and bounces off the mirrors, can actually be corrected down to just 1% of a single pixel. 1%! That translates to roughly 1 milliarcsecond. Getting a subpixel software correction like that is just an absolute triumph of astronomical engineering. And here is exactly why that 1% correction is absolutely crucial. Without it, we face a pretty terrifying worst-case scenario. Imagine we allow a tiny, maximum allowed 60 milliarcsecond rotational offset right at the center of the detectors. Because Roman's field of view is so incredibly vast, that tiny little error at the center multiplies as you move outward. By the time you reach the farthest pixels at the outer edges of the detectors, that 60 milliarcsecond error balloons into a massive 545 milliarcsecond offset. That is nearly 5 whole pixels. An error that massive would completely wreck the precise photometry, our ability to measure the exact intensity of light, which is what we actually need to extract real science from the images of those billions of galaxies. Which brings us to the ultimate point of all this insane effort. When you combine a massive 0.281 square degree view of the cosmos with subpixel software corrections, an impossibly precise guide star catalog, and algorithms that can intelligently dodge cosmic photobombers, you create the ultimate astronomical machine. It really leaves us wondering, right? What unimaginable secrets about the expansion of the universe and the worlds orbiting other suns is the Roman Space Telescope finally going to bring into focus? Think about what humanity is going to uncover now that we can literally track the heavens down to a fraction of a single pixel. I hope you found this explainer as fascinating as I did. Keep looking up and never stop wondering about the incredible mechanics that let us see the stars.